Hello everyone, and thank you for joining us today. In today's webinar, we will be discussing our product HFWorks. We will demonstrate optimization of metamaterial structure for high-gain array antenna. Before discussing today's agenda, let me introduce ourselves. My name is Hassan, and I'm a sales engineer in HFWorks. And we will have my colleague Nasreen, who is a senior application engineer in HFWorks. She will be delivering the technical part of today's webinar. Our agenda for today is the following. I will briefly talk about our solution advantages and benefits and what products we offer. Then my colleague will present the technical part. At the end of the technical presentation, I will talk about licensing, services, and various learning resources offered by HFWorks. The idea that lay behind integrating electromagnetic simulation software into a CAD tool is innovative and fresh. So the idea is, what happens conventionally is, if you want to use a new simulation software, you have to put tremendous effort and amount of time to learn a new modeling environment. First, and only after, you will be able to start your simulation. Furthermore, usually modeling features inside a simulation software is very primitive. It's not meant for complex geometry. So why don't you get the privilege of using most arguably best CAD tools in the world, either Solidworks or Inventor? Even if that is not the case and you already use your own CAD tools, so now it's time to import your model into your simulation tools. But what if you want to change different parameters and geometries and see the result on the spot? Yes, you should export and import a lot of times. You have to switch between two software multiple times to reach the optimum result. That's why it's better to do everything, modeling and simulation, all in one place. So that was the idea to address this issue. We are just inside your CAD tools such as SolidWorks or Autodesk Inventor. For example, for SolidWorks, which is the most powerful CAD tool with motion features currently, there were other plugins for other applications like mechanical and structural, but nothing for electromagnetic analysis. We honorably filled the gap, and we are offering 4 different products for our valid customer users and customers inside this CAD tool. Our products are gold certified by Dassault Systems SolidWorks Corporation since 2008. So we offer 4 products with various add-ons covering a wide range of frequency. Our first product is called EMS, which is used for electric and electromagnetic field modeling for low-frequency applications. It covers many applications like insulators, cables, bus bars, permanent magnets, actuators, circuit breakers, transformers, motors, and so on. The second product is HFWorks, which is used for electromagnetic simulation of RF, microwave, high frequency, and high-speed electrical and electronic devices. It covers applications including a wide range of antenna, resonators, filters, connectors, waveguides, and etc. Our third and fourth product, the first one is HFWorks 2D, which offers static analysis and covers the simulation of planar and axisymmetrical geometries. Our latest edition is Motor Wizard, which is a template-based motor design software. It offers analytical and finite element analyzers for BLDC and PM motors. In addition to these solvers, we offer multi-physics solutions like thermal, motion, linear statics, and circuits. In today's webinar, we will utilize HFWorks software to do rapid optimize of metamaterial structure for high-gain array antennas. I would now request Nasreen to take over and present the next part of this presentation. Thank you.
Thank you, Ehsan. Hello, everyone, and welcome to this webinar titled Rapid Optimization of Metamaterial Structures for High-Gain Array Antennas. First, I want to thank you all for joining us today. I'm Nasreen Selmi, a Senior Application Engineer and Technical Support at HFWorks. Let's have a look at our agenda of today's webinar. We will start with an overview about HFWorks tool inside Solidworks. Then we will go through a quick introduction about metamaterials. Next, we will talk about the models. I will present a live demo of HFWorks interface and workflow, and we will go through a detailed analysis of results. And at the end, we will conclude by answering your technical questions. Simulation lets you predict behavior virtually. By creating models and doing simulations, we can bring our designs to life before they are produced. HFWorks is one of the best electromagnetic simulation tools. It's a full-wave 3D electromagnetic field solver. It's fully embedded inside Solidworks. It uses Solidworks as a CAD. It's based on frequency domain finite element method, so it covers the whole band of the high frequency, going from few megahertz to some terahertz. It's also coupled with thermal analysis coming from the Joule effect. HFWorks presents 4 types of studies. The first one is antennas, to simulate the electromagnetic behavior of arbitrary 3D single or array antenna structures. As parameters analysis, to compute the frequency response of complex 3D passive RF, microwave, and millimeter wave components. Time domain reflectometry or TDR, to study the discontinuities and coupling effects in connectors, adapters, and cables. And resonance, to calculate multiple resonant modes. Also, HFWorks comes with an integrated electrothermal analysis, allowing to compute the thermal behavior of your structure due to the dielectric and conductor losses for multiple scenarios. So, to simulate any model inside HFWorks, first we have to create the geometry or import an existing 3D geometry from another CAD. Next, once the model is done and ready, we switch to Simulation tab and start by the pre-processing steps. It means assigning the material to each body using HFWorks material library, or the user also can create its own material library. Also, we can do parametric study or multi-configuration study to play with the geometry. And finally, the meshing step, using different mesh options provided by HFWorks for manual and adaptive meshing. Then we solve to extract the different output parameters. It can be the circuit parameters or 3D and 2D field plots. And finally, if you want to have the multi-physics coupling, it can be done using a post-processing thermal and structural coupling, allowing the thermal stress analysis of your device with the ability to rerun your electromagnetic parts with the final deformed structure. Our design today will be metamaterial-based antennas. But first, what is metamaterial? This word is a combination of meta and material. Meta is a Greek word which means something beyond, altered or changed. Metamaterials can have their electromagnetic properties altered to something beyond what can be found in nature. All natural materials like glass or diamond have positive electrical permittivity, magnetic permeability, and an index of refraction. The electrical permittivity and the magnetic permeability are the main determinants of materials' response to electromagnetic waves. In metamaterials, both these material parameters are negative. The refractive index of the material is also negative. Another strange property of metamaterial is its reverse Doppler effect. Metamaterials are artificial structures, periodic, quasi-periodic, and non-periodic, that allow to tailor the propagation of electromagnetic waves. In this word, metamaterials specifically mean a periodic array structure added in order to improve the antenna gain. As shown in this figure, the metamaterial structure is composed of a very thin copper grids with square lattice whose period is equal to 7.6 mm in the X and Y axis. Let's move to the antenna design with metamaterial. The structure of the circular waveguide antenna is shown here. It works at 11.5 GHz. The metamaterial structure is located at a distance of 9.5 mm from the antenna aperture. The spacing between the two layers of metamaterial in Z-axis is very sensitive to the antenna results, so it's necessary to analyze and optimize the effect of the spacing between these two layers. So during this webinar, we will go through different steps, starting with analyzing a single antenna element with and without metamaterials, and different techniques of geometry optimization in HFWorks. Then we will move to study array antennas and investigate different types of results. But before moving to the simulation results and revealing what we got after solving structures, let's have a quick demonstration of HFWorks interface and workflow. So here we are. This is Solidworks Interface and this is my antenna design. You can see here I have built a complete model where I have actually the circular waveguide model, which is fed by a coaxial probe and surrounded by the air parts. So this is inside SolidWorks. This is an assembly, and SolidWorks has these design tables which allows us to create with these different parts different configurations. So you can see here I have essentially two configurations. I have a configuration without metamaterial structures, what I'm showing now. This is the active configuration. And I have another configuration, the antenna with metamaterial structures. In case I want to see an alternative configuration, always within the same design, I can just show the second configuration. So in this case, metamaterial structures are added automatically. So as we can see, this is a nice and powerful feature inside SolidWorks that allows me to switch between two different models and study them within a single document. So now, among these designs, for simulation purposes, we're going to use HFWorks. So to do that, from the list of add-ins here, you have to check HFWorks. It's already checked here. Then the HFWorks Manager tab will be appeared automatically here, and also HFWorks is accessible from the Tools menu under EMWorks Products HFWorks menu. The process of getting simulations in HFWorks is called studies. What we see here is the name of our assembly, circular waveguide antenna with metamaterial. And under the assembly there are different configurations. So if we want to study this antenna, we will create an antenna study. And now we have to define the study properties, starting with the first tab, General Properties. We have in this box the name of the study that we can modify it. We need to choose also the type of solver, direct or iterative solver, and the accuracy type, normal or high accuracy. We have here parametrization to create a parametric study. Next, we have the port solution to solve the port solution only or save 3D field data. And to get the safety factor, we have to check this option, compute fields to break down levels. The second tab, frequency sweep, that allows us to define the frequency sweep. We can set the sweep type, either discrete, fast, or single point. Then we set the frequency band, the start and end frequency, and also the number of points. The list of frequencies will be displayed automatically here in this table. Next step is the meshing. HFWorks presents two types of meshing: manual meshing for experienced user that can predict the error location in the structure. It helps the user to control the density of the generated mesh, so it's recommended for large problems in order to reduce the number of elements and to get a faster solution. And we have also adaptive mesh, which is a dynamic process that recursively refines the mesh in regions of high error. For each meshing technique, we have different options that should be filled carefully by the user. The final tab is for the coupling analysis. So here we have the thermal coupling. Once you defined all these parameters, you can just click on Validate, and a new study is created automatically. And then comes the process of simulation, which is really on 3 steps. We need to define the material properties for each part. We have to apply the excitation and boundary conditions, and we have to generate the mesh. So the material application step is standardized. We have a built-in material library here. We have different materials, and you can also add your own material by creating a new material library. So here we can pick a material for each body and part for the assembly. Next step is to set the boundary conditions. We have to apply the port. It can be wave port, external or internal wave port, and damped ports. We have also perfect electric conductor and imperfect electric conductor for lossy conductors, and the radiation boundary condition to apply it on the outer faces of the air part, and other boundary conditions. Then the meshing step, which depends on the meshing technique that you already chosen. For adaptation, you have only to click on Create Mesh, and in case of manual meshing, you have to create and to define mesh controls. And finally, you can just right-click and run the study. I already have a solved study. We have here a new added section that contains the results, the folder results here. So under this folder we have the 3D electric field and magnetic field plots, loss densities, total loss, to compute conductor and dielectric losses, port fields. For 3D field, electric field, we have different types of plots. We have the fringe plots, the vector and line. For fringe, for example, we can do a section clipping plot to show the field inside the part. So this is our electric field. From the definition tab, I can show plot on selected entities. Can choose here the air part. And I can also check ignore touching parts to ignore any touching parts. From the section clipping tab, I can add more than one section, and I can define the plane section clipping. I choose here the right plane. I can plot on section only, and I can play also with this distance. The distance between the origin of the model and the section clipping plane. I can also animate my 3D plots by clicking here on animate. We can animate versus phase or versus section cut. We have also the port field solution. We can display the electric field on the port, as well as the port magnetic fields. We have another folder, circuit parameters, which contains all the main results. We have the tables, the results table that contain the generalized S matrix, renormalized S matrix, impedance matrix, port results, the ZPI, ZPV value, and gamma value. We can also create our own table by specifying the needed parameter from here. Can add S parameter and choose the unit. Can also add VSWR, click OK. We have also plots, 2D plots and Smith plots. The last folder antenna is antenna parameters. It's only added for antenna studies. We can add and create a new far field case. We have here the port configuration to set the excited mode, the power of the port, and the phase value. And here we have the far field options by which we can define the start and end and step values. And we can click OK to run this far field case. I have already one far field case. From the results table, I can check different results, the maximum directivity, the maximum gain, the total efficiency. I can also create and customize a new table versus frequency or versus angle, and choose different parameters, and also add from different sources. And click OK here. My table is created. From the plots, I can add 2D plots or polar plots, 2D polar plots and 3D plots. I have here the gain pattern of my antenna. And I can also add the 2D polar plot of the antenna versus theta. I can activate the other configuration, antenna with metamaterial, from the study, since I have already solved studies. Right click and click on activate configuration. The two metamaterial layers are shown now. They are located at 9.5 mm from the antenna aperture. Each layer is composed of 9 by 9 cells. The spacing between these two layers in z-axis direction is very sensitive to the antenna radiation and to the distribution of the electric field. So we need to find an optimized value that achieves the best results in terms of return loss and antenna radiation characteristics. In order to study different values of the spacing between these two layers, the parametrization feature is used. That allows us to run multiple analyses automatically and then examine the results and to define the parameters. Only model dimensions can be parameterized. To access to the parameters window, right-click on the root node in HFWorks Feature Manager and select Parameters. This dialog box appears. Contains the predefined parameters with default values, unit, and types. You can pick other parameters by opening a sketch to get dimensions. Once I have defined all parameters under Parametrization folder, I will find Design Scenarios. HFWorks comes with two types of parametrization, physical dimension parametrization and wavelength parametrization. For physical dimension parametrization, these types varies the dimension using the values mean, max, and step. So push generate scenarios button to get all the scenarios based on all possible combination of the defined variables. From the list of those generated scenarios, you can choose the scenarios that you want to solve. For example, in my case, I just include 3 scenarios, scenario 1, 2, and 5. And now after solving the study, I can compare the results for different scenarios by creating some plots and including all the scenarios. Here I plotted the different return loss of the 3 scenarios. From these results, the best scenario is scenario 5, which corresponds to value D1 equal 9.5 millimeter. And also I can compare the radiation characteristics for different scenarios from the results table. Here I can check and choose the scenario and the results will be updated, or I can easily create a table from the tables folder and choose the parameter and all scenarios. So from this table we can compare the maximum gain value for scenario 1, 2, and 5. As shown here, the maximum gain value is obtained using the scenario number 5. So as a conclusion, the gain of the antenna is improved by using the metamaterial structures. Also from the 3D electric field plots, we can notice that the metamaterial structures congregate the radiation energy, so the gain of the antenna increases while the side lobe level decreases. I can animate this field. Versus phase and versus scenario. And here is the animation of the electric field versus phase on the air part. And now let's come back to our presentation to investigate the obtained results. In this slide, I summarized the most important results, the plots of return loss for different scenarios, as well as the maximum gain values at 11.5 GHz that prove that the optimal scenario is scenario number 5 with a spacing equal to 9.5 millimeter. The figures here show the electric field distribution in free space with and without metamaterial structures. We notice here that the 2 layers of metamaterial structures can realize congregating the radiation energy. So the gain of the antenna increases while the side lobe level decreases. The simulation results show that the maximum gain goes from 7.9 dB to 11.5 dB when adding metamaterials. A conventional other method to improve the antenna gain is to use array form. So here I built from the single element 2-element array antenna and 4 elements array antenna. I will switch now over to Solidworks. I have here the first array antenna with 2 parallel elements. I used also multi-configuration to study this array without and with metamaterial structures. Moving to HFWorks, I have already simulated and solved studies. So here from the results table of the far field case, at 11.5 GHz, the antenna realizes a maximum gain of 14.6 dB. Here is the gain pattern in dB of the antenna. Moving to the other example of the array, 4 elements antenna array. I did the same thing. I have 2 configurations. Here metamaterial structure is composed of 9 by 25 cells. This antenna realizes a maximum gain of 17.8 dB. So we can notice that there is an improvement of gain from 2 elements to 4 elements antenna array. Here I summarized the simulation results. As we can see, the gain of a circular waveguide array antenna with metamaterial structure have to about 3 to 4 dB addition in comparison with those of conventional antennas. For 2 elements array antenna, the maximum gain goes from 11.9 dB to 14.66 dB when adding the metamaterial structure, and for the 4 elements array antenna, the gain goes from 13.4 dB to 17.8 dB. And we notice also that there is an improvement of antenna gain from 2 elements array antenna and 4 elements array antenna. So with that, I like to conclude this presentation. We saw how HFWorks presents a powerful tool to analyze antenna models and complex geometries to investigate radiation characteristics. Also multi-configuration and parametrization features that helps to optimize your design and study different scenarios within the same project. And how metamaterial structures improved antenna radiation characteristics. This technology can be applied in various antennas to improve their radiation performance. I would like to thank you all for joining us today. I'm going to pass my screen to my colleague Isan.
Thank you, Nasrin. Thank you, everyone, for bearing with us, and I hope you have learned enough for this webinar so far. Let me briefly touch upon the licensing structure offered by HFWorks. We offer 3 different programs: commercial, academic, and startup programs. Each program has its own benefits and requirements. Within the commercial program, we offer perpetual or lifetime licenses, while our licensing structure is usually annually based on the rest of the programs. We have a combination of free and paid licenses for students, academics, mentors, lecturers, and professors based on the program they choose. And for startups, we are offering a very interesting plan for paying in installments. For the learning resources, HFWorks offer various various free learning resources. With the software purchase or trial, users can access to the demo viewer section of the software, through which they can access many predefined, ready-to-solve models and examples and tutorials. In addition, we have regular webinar series on trending electromagnetic topics. Moreover, we post several application notes, blogs, and videos on our web page and social media channels regularly. We also offer paid customized training sessions to all users of HFWorks software. Our support service is the strongest point that I can mention in this presentation. We always have your back before and after sales. That is including one-to-one web demo sessions to shorten your learning curve, or even do benchmarking with the model that you shared with us. Also, we offer consultation and design engineering services, even come up with a new design as per your requirement, or refine and optimize your existing design. These are only a couple of our valued clients. These big names are coming from different industries, showing our comprehensive and extensive solution. At the end, I encourage everyone to try our software and experience its capabilities. We offer 2 weeks of free trial access. Visit our webpage, hfworks.com, go to our contact page, fill in your information to submit your request, and we will contact you. At the end, I would like to thank you all on behalf of HFWorks for participating in this webinar. Feel free to contact us after this webinar to get more information on our products. Thank you very much, and have a great rest of the day.